Welcome to lesson 2.3. This lesson is very different from everything else we've done in chapter 2. So far we've done a lot of graphing. 2.3 is actually kind of split in half. In the first half of this lesson we're going to talk about two equations. And in the second half of the lesson we're going to talk about two other equations. So in the first part of this lesson we're going to talk about length of a circular arc, which is this equation, and area of a sector of a circle, which is this equation. So let me show you what these two things mean on this example. Length of a sector, I like to think of as the pizza crust. It's how long the pizza crust is. It's a length. Basically, it's a portion of the circumference. Versus area of a sector is how big is the pizza slice. That's area of a sector. So, length of a circular arc is your pizza crust. Area of a sector is your pizza slice. Now, these are the two equations we use for them. One other thing to note, R obviously stands for radius because we're talking about circles, but both thetas must be given in radian measure. These equations only work if your angle is in radians. So if your angle is given to you in degrees, the first thing you're going to have to look at is converting it. So understanding those two equations, let's try some examples. Example 1. I want to find the arc length along a circle. So here's my circle of radius 10 units. And it is subtended by an angle of 215 degrees. So here's my 215 degrees. And I want to find the arc length. So I want to find the pizza crust around this circle. So since it's arc length, that's going to be S equals R theta. My R is the 10 units. My theta it gives me is 215 degrees. However, we know that theta must be in radians. So let's do conversions. You may remember conversions from chapter 1. Anytime we do a conversion, we multiply by a complicated looking 1. Now, what you want to cancel is going to go on bottom, and what you want to end up with is going to go on top. So then that way, the degree symbol on top and the degree symbol on bottom cancels, and I end up in radians. Now for my complicated 1. I think, how many radians in how many degrees? Well, I know there are pi radians in 180 degrees. That's my complicated looking 1. Pi radians and 180 degrees are actually the same thing. So they cancel each other out. That's a 1. And because my degrees canceled, this is now in radians. So what we can do now is remember this 215 is technically over 1, and this 10 is over 1. So in your calculator, you can just use your fraction button, and in the numerator of your calculator, you'll multiply across. So do 10 times 215 times pi in the numerator. And in the denominator, you multiply across 1 times 1 times 180. And you just type all that into your calculator, and you should end up getting 37.52 units long. So that's how long my pizza crust is around this portion of the circle that is this big. So that's a little bit of practice with our arc length. Let's try another one. We're actually not going to do this. So we're going to talk about Mercury. Mercury orbits around the sun, and we're going to pretend, just for the sake of this problem, that the orbit is a perfect circle. In actuality, the orbit's an ellipse. We're going to pretend it's a circle for this problem. Now, let's say my Mercury is right there. There's my cute little Mercury. And we know that Mercury is 36 million miles from the sun. Now we have in 1 Earth day, Mercury completes 0.0114 of its total revolution. How many miles does it travel in 1 day? So if we're looking for how many miles that this little planet travels, we're looking for the pizza crust. We're looking for the distance along the edge. How many miles is it traveling around the sun? So since this is a pizza crust problem, I'm going to use S equals R theta again. I know my R is 36 million miles. I'm going to include the units on that. And the theta it gives me is 0.0114 revolutions. That's how much of the revolution it goes around. Now we know theta must be in radians. So once again, I'm going to multiply by a complicated looking 1 to convert this from revolutions to radians. So I'm going to put revolutions on the bottom so they'll cancel, and radians on top because that's what I want to end up with. Now I think, how many radians in how many revolutions? Well, I know there are 2 pi radians in 1 revolution. So there's my complicated looking 1. And now, because the revolution's canceled, this angle is in radians, which is what I wanted. So same thing in your calculator, multiply all of these on top, 36 million times 0.0114 times 2 pi, and the 1's on bottom. And if you put all that into your calculator, you should get pretty close to this. So in 1 Earth day, Mercury travels about that many million miles. Let's do one more example with this. In example 3, I have a lawn sprinkler. This lawn sprinkler is spraying a distance of 20 feet while rotating 30 degrees. So it's watering this whole piece of grass. We want to know what is the area of the sector of grass that this sprinkler waters. So now you can see I am now dealing with a pizza slice. I'm dealing with area. So that's going to be this equation. Now the theta we're given is 30 degrees, but once again, theta needs to be in radians. So I'm going to do a conversion to convert from radians to degrees. My degrees on top and bottom cancel, and now I'm left with just radians. Then I have r squared, and I know my r, the radius of this circle, is 20 feet. That's how much it goes around. So once again, I can just put into my calculator. Here we go. So on the numerator of my calculator, I have 1 times 30 times pi times 20 squared, all in the numerator. In the denominator, I have 2 times 1 times 180 times 1. And my angle is in radians, which is what I want, and there's my r squared. So if you type all that into your calculator, you should get this. And because this is an area, it's two-dimensional, we have 104.72 feet squared. Because it's two-dimensional, we square the feet. And that is the first half of our lesson. Everything with length of a circular arc and area of a sector of a circle. In the next half of the lesson, we're going to introduce 2 new equations that we'll talk about for the second half.